Well, good morning, everyone, and thank you very much, Richard, for your interesting presentation. Um, People who have questions to Richard, maybe you can forward them by sending it to our chat. But for the moment, we have some questions already. One of the questions that was raised to me, if it is right, you will see it now on the screen. The questions that we received is,
We cannot see your screen, Hans.
you cannot or you can?
We cannot.
Then you get it now.
No press. Oh, it's coming.
Yes, now you should see it.
Perfect. Yeah.
Okay. Well, then here you see some of the questions that we have received over the last couple of weeks. One question was raised to me, but I think that maybe Richard can also add something. The question was, are the occupants considered in tackling the problem of the gap between measured and simulated performance? If yes, how? Well, let me start with giving a part of the answer to this question. Of course, occupants can be considered in tackling the problem. That has to do with what kind of data has been collected from measurements. You can imagine that the people are not always in the building available, so there are distinguished moments that the data is dealing only with the building itself and not with the occupants. You can imagine that it is in a period of holidays, for example, that the house is put in a certain condition and there are no people in the house. But of course, also you can have some other data that is dealing with it. For example, the consumption of water. When there are people in the building, then they consume water, and this is giving a kind of information about what they are using. Water can be heated, etc. When people take a shower, this is all kind of consumption of the date of the energy that it is used by the occupants. More problematic is when they open the window, when there is more ventilation. That has to do with the measurement part. If you consider then the simulated part, well, of course you can model the occupant's behavior, and there are several ways to do that. Some of these modeling works are presented. We have been dealing with that in other projects as well. There is information about how to deal with that, but there is of course the occupants' behavior during the night, during the day, when they wake up, when they go to sleep in the evening, when they come back from work, etc. So you can have a kind of a standardized modeling calculation of it. So if the problem of the gap between measured and simulated performance is coming also from the occupant, but it is not always clear if the occupant is the reason of this gap. And there are also studies that have been carried out by laboratories that show that even the construction, the way of construction, the way of renovation is giving a difference between the calculated value and the measured value for the performance. When we are looking into smart metering, maybe I go and ask Richard if he can have some additional information about how to tackle the problem of the gap between measured and simulated performance. Richard.
Yeah, so I'm not certainly an expert in occupancy, on the social side of occupancy, but in terms of data, so the latest innovations in the smart thermostat world are certainly localized TRVs. So the local TRVs that will basically do time and temperature in each room. A lot of those have window opening sensors, and they also have the ability to start to look at learning behaviors in the building. So you could look at pulling the window opening data from those devices, which is quite straightforward. And also where you've got devices such as Tado and Nest that claim to learn your occupancy, then they've got pretty good data sets in terms of when they think the building is occupied and unoccupied. But yeah, smart meter data can do pretty much the same. Flurries in activity indicate that the building is occupied generally. Heating maybe not so. The best one that we've worked with as an indicator for occupancy is water. No one flushes the toilet if they're not in the building. So that's quite a good one to look at as well.
Okay, thank you. I hope that the answers that we have given is an answer that you can live with. Then we go to the second question. The second question is for Peter Bacher. Is the Kalman filter based on Bayesian analysis? Peter, you can get the floor to give an answer to this question.
Thank you, Hans. So can you hear me?
Yes.
Can I become the presenter so I can share my screen?
So I have to.
Yeah, I think
Yeah,
now.
you are there. Yeah.
Then I will say do like this. I think you can see my screen now.
Yes.
Good. Yeah. So oh, that was the wrong one. But I want to just to explain this. I will spend some 15 minutes, 20 minutes, just explaining how yeah, the estimation that I introduced in the lecture is working. So basically, you have two approaches. You have frequencies and Bayesian analysis, and it's not always clear what is either. But as such, the Kalman filter you can say is Bayesian, but we use it in a way where we would say that we are doing frequencies analysis, and what we're doing is what is called likelihood. And it was a little bit fast last week, but I will just quickly show an example here. So I hope that that will make sense, because basically likelihood and maximum likelihood is a very strong statistical technique that we use for a lot of, you can use it for all kind of different applications, as I also tried to explain last week. But I'll just show a quick example to give a little bit more understanding of that. So basically what we need to remember here, I think you can see my mouse. Here's the most simple setting that we can, or like the basic setting of doing statistics. So we basically have a population and we want to find out something about this population. So we want to find out something about the mean, the average of this population. We cannot, here we see sort of height of humans. We cannot say measure everyone. So we just take a sample. We take n observations in our sample. And now our best estimate of the mean of the population is the mean of the sample. And well, that's a very simple statistical method. We just calculate the mean of the sample, and that actually works in many settings. But what we can do that in different ways, and one way we can do that is simply by taking. I mean, we say we set up a model like this. That was just what I explained. One way, yeah, we could calculate the average. Another way of doing this, of obtaining estimates of the parameters of the population, would be to use likelihood and use maximum likelihood technique to estimate the parameters. And basically, in our model here, we have two parameters. We have the mean, the average of the population. We have the standard deviation. And if we assume a certain distribution of our population, then we can calculate this expression, which is what we call the likelihood. And it means take the probability density function. So take the probability function of the values that we actually observed of our sample, given some values of the two parameters, the mean and the standard deviation. So take the normal distribution. So basically it says multiply these probabilities. And basically now we will take the normal distribution probability density function and look up the probability of observing each value in that given some value of the mean and the standard deviation. So we have the data, and then we look up the probability. And when we do that, then we don't call it a probability, then we call it a likelihood. But it's using the probability function of the model. And basically, what we'll do is that we'll then try here to estimate the parameters. We will then take the likelihood, and then due to numerical reasons, we will take the log to the likelihood and then the negative, and then we will minimize this as a function of the two parameters. So this will give us the same two parameter values that will maximize this probability function, this likelihood function, where we multiply the values of the probability density function. So let's look at an example. Now I go to R. I don't know if you know this, probably not, but what you see here is now I set a value for the average of the population. I say the average, the mean of the population is 150. The standard deviation is 15. And now I'll generate a sample from the population of 100 observations. So I just now generate 100 values from this normal distribution, random values independent of each other. We can calculate a histogram here and see the histogram here and how they actually compare to the population distribution, which is the black line. All right, we have a sample. We want to figure out something. Now we know the true values. They are 150 and 15, but we want to estimate it using the sample. So what we can do is define the negative log likelihood. So as a function of the two parameters, the mean and the variance, then we calculate this. We look up in the probability density function and calculate the likelihood of each observation, and then we return that. And now we pass that on to an optimization function. We'll do it here, and then we'll do some. It's a little bit messy code, but now you'll see what happens once we run this. We start at some points. We start saying the values are 0, both of them, and then we use an optimizer to optimize the negative log likelihood. So you can see here on the right plot, the likelihood, it decreases because it's a negative value. And we want to find, and now the blue one is a true one, and the black one is the probability density function with the two parameters that we end up with. And finally, the optimizer says we estimate the mean to 150.8 and the standard deviation to 15.1, so close to the true values. And what we can do is that, another way to view this is to simply look at this likelihood function and see how the optimizer steps through. This is the likelihood function, and we can see that on the negative likelihood function, so we can see that the minimum is at 150. And same wise for the standard deviation. So this is the point, the true point, and now we're finding the point which minimize the function. So using this technique, we can actually estimate parameters in any model. Only thing we need from a model is it defined like this, that says our observations are taken in a certain way. It can be a function of anything, other variables, and there's a certain error which has a certain distribution, and then we can write up the likelihood function, and then we could do this maximization or minimization of the negative log likelihood function. And then we obtain the parameter estimates. And that's exactly what we do in the package with the CTSMR, where we do this in a setting where we have data from a dynamical model. And in order to estimate or to calculate the likelihood function in this setting with where we have the differential equations or stochastic differential equations and the system equation, the measurement equation. Then we use the Kalman filter to calculate this likelihood. And the way that the Kalman filter work is, it's kind of depicted here, but I'll try to make a short, I'll draw my way through and try to explain it. So basically, if we write up the model, then we can write up the likelihood function and we can do the optimization of the parameters and thereby get the likelihood estimates of the parameters. But we need to be able to fit the model to the data and calculate this likelihood. And what happens is, I'm just going to draw it. And again, you can't really interrupt me with questions, but I'll just hope that it makes sense what I'm saying. Let's write up this very simple model, dx. It can be any model, and now this was just with one state, and I will just say that the system equation of this is like this. So it's a first order model, AR model, but we doesn't matter here. And we have some the stochastic part, but doesn't matter really either right now. The point is that now we have a model, and we would also have a measurement equation. So we would write, okay, we just observe at k step, we observe the state at that time, and we have this measurement error. But anyway, what I want to explain is how the Kalman filter works. So the Kalman filter works such that we start somewhere. We need to have an initial state. So this would be t0. And then from that point in time, we'll use this model. We'll use the system equation to predict the states. So what we start out with is to say, we keep track of the states in a state vector. So we say here at time t, given information up to t or t0, then we know, sorry for the noise here, but I'm sitting in some other place. We know we have, this is we need some starting initial condition of our state. So we say we're here. So this is the value of x. And then we do a prediction. We do a prediction using our model. It predicts maybe to here. And then I found another color. So this is the prediction using this model. We will predict using this model. And then we will, this will be our prediction of the states. So we'll write x t plus 1, say that the step is 1, given t. So this is our, we can put a hat on it. This is a prediction of our state, the one-step prediction of our state. So we can write, this is at t1. We could write t0 here if we want. This is the prediction. And then we have our model, and our model says that this is a normal distribution. The state, our prediction has some normal distribution. And in order to get that normal distribution, the width of that, then we keep track of the covariance matrix of the states. And we keep track of that, and we actually also do a prediction of that. And over here, at the starting point, we also needed an initial value of the covariance matrix. So we had that. And so our model also tells us actually how the uncertainty, the standard deviation of this, or the variance of this, evolves over time. So we can put these. We know that we actually, to begin with, had one normal distribution, but it actually, it's more narrow than the other one. So it starts here, and then over time, the variance actually increase. So now we know that we have this normal distribution, and then we go in and we take the measurement. And let's say that we have the measurement here. So now this is actually the state. So I'll just write xt given t, the measurement. I could write y, but now this is the measurement. And then what we do is to calculate the likelihood function. We go into this value and take this probability, which is then a likelihood. We take this here, and it's actually the probability density function of observing our observation, given the inputs and everything, and the parameters in the model, and so forth. The one step ahead prediction, the probability of this observation given our model. And once we have those, and when we have those, then the Kalman filter magic comes, because the Kalman filter in what we call the update state, it will then, this was our prediction, and now we will, this was our prediction, this was our observation, and now the Kalman filter will calculate an updated value, which will lie in between here. Please, if it's, okay, it will. So here, maybe somewhere in between this, depending on how much we trust or the variance of the prediction and the variance of the observation, then it will find an update of the state. So it will be our updated state. And it will also calculate an update of the covariance. Okay, so I could write T1 here. But what we see is that, this was the same as we had in the previous step. So now we will repeat this process again, and then we will, from here, do a prediction and calculate again, the one-step prediction and the one-step covariance matrix, and then we will look up the probability density function of that one-step prediction, and we'll add that to this, and finally we'll when we multiply all these, so y of t1 and so forth, we'll do that for all the points, and this is our likelihood. And then we will so we will run through one time with some given parameters. We'll run through the whole data set with some values of the parameters using the Kalman filter, and then we will change the value of these and optimize these. We'll optimize these parameters such that we maximize the likelihood function or minimize the negative likelihood function, and then we get our estimates once we do that, as I just showed before. So this is sort of trying to explain how the Kalman filter works, doing this. So I spent years playing around with this, so now I have a pretty good understanding. And the magic of the Kalman filter is in the update step, where it does a weighting such that it produces or does the least squares estimates of the state vector. So actually, Kalman filter is a least squares technique. All right. I hope it gave some kind. Got really messy this figure, but I'll share this example and the code and the slides so you can look into them. Yeah, I hope it was meaningful. I don't know if you have some questions for the questions. I'll try to see in the Q&A box. Again, it's a little bit fast, but I hope that you have an idea of where to sort of, look for more information on the Kalman filter and all these techniques.
Well, Peter, thank you very much.
Okay.
I will try to share my screen again.
Yeah.
Yes. Thank you very much again. I think it was quite an extensive answer, and I hope that the people who raised this question are happy with your presentation. So for the next question, we go to Aitor. Aitor is asked also to give an answer to the question on the surface temperature measurements. Aitor, can you take it over from here?
Yes, thank you, Hans. Can you hear me?
Yes.
Perfect. So I will share my screen.
Yes.
Can you let me share things, Hans?
I have stopped my sharing, so you should be able now to share it.
Oh yeah, you need to move the ball to it. Or, yeah.
Yeah.
Thank you, Hans.
Now you should be able to share. Yeah.
Yeah. So can you see the presentation?
Yeah.
Thank you. Okay, so this was the question I received about the first presentation I did in the first webinar. On the internal surface temperature measurement, how did you consider overheating on captors exposed to solar radiation, especially on captors on internal surface of glazing? That's the question. Is a very good question because the temperature sensors used for measuring surface temperatures are usually of the type you can see here in the right. Yeah, this is a thermoresistance. It can be also done with thermocouples, but this surface, yeah, this sensor is usually sticked into a surface to measure its temperature. And there we have a problem because if this sensor is not behaving exactly as the surface where you want to measure the temperature radiation, you might have deviation between what is actually the real surface temperature and what you are really getting. Yeah, that's a very good question, and it's much more important on glazing. I will explain this with an example. I think you have used. Some of you have been working with this example. This is a the round robin text box. Yeah, this is behaving as a small building, and there were a lot of sensors measuring this small building, including surface temperature in this glazing and surface temperatures in the internal and the external surface of each of these walls. So here, yeah, this test was done really consciously and very well prepared because this is a correct measurement of surface temperature in the inner surface of this box. The inner surface of the box was painted in black. So if you want to measure the heat flux or the surface temperature, the red one is for measuring heat flux, and the rectangular one is the surface temperature sensor. You have to paint it exactly. You have to, first of all, paste it really well to have a perfect contact or as much as perfect contact as you can. And finally, to paint it in the same color with the same paint of the surface. Why? Because this way, this surface and this surface will have a similar emissivity. So they will behave in a similar way in both heat exchanges that occur in the surface of these two, the real wall and the surface of the temperature sensor. They will exchange heat by convection, and they will exchange heat by long wave radiation and by short wave radiation with the surrounding. The short wave radiation is actually the solar radiation. So this surface and this sensor will have only the same temperature when the emissivity of these two surfaces for both the long wave radiation and the solar radiation, that is the short wave radiation, are similar. When we have windows, we have a problem, because if we have a window, this surface will never behave as the real glazing. So the real temperature that is measuring this surface temperature during the daytime when solar radiation is striking the window will be probably different to the glazing real temperature. Why? Because the glazing surface has a different emissivity for the long wave radiation than the one it has the temperature sensor, or as you can see here, the round one, the heat flux sensor. So actually, when you are using surface temperature or surface heat flux measurements in a semi-transparent element as windows, you are not measuring the exact surface temperature of the window. You can do it here in opaque surfaces, but when you have glazing, it's very hard to measure them correctly because the behavior of the sensor surface and the behavior of the glazing surface should be the same. And here you have an example. Yeah, these are the surface temperatures of the box in the external surface. This is we have the east, west, bottom, top, and north faces. When solar radiation strikes in the afternoon, we have a peak in the temperature in the afternoon in that surface, in the west surface, and in the east surface, you have this small peak in the morning. But if we see the glazing temperature in the external part, we can see that the glazing has a very different behavior of thermal resistance compared to the other walls. So actually, since we were heating up the internal part of the box, the window external surface temperature is much hotter than the outer surface temperature of the walls. And when the solar radiation strikes in the south face, we can see that the surface temperature measurement might go up to 42, 43 degrees. And probably in this area where we have solar radiation, the glazing temperature is not exactly the one given by this sensor because the behavior of the emissivity of the surface of the sensor is not the same as the glazing one. But at night, when there is no solar radiation, probably this surface temperature of the glazing is very close to the glazing temperature, even if the emissivity for the long wave radiation is not exactly the same in the surface of the surface temperature and in the surface of the glazing. So I hope I have been able to answer more or less to this question. And well, if you have any other question or you want more explanation on this, you have my email in my first presentation, so you can contact me.
Thank you very much, Aitor. Now I like to return to my screen. So we go. So some other questions have been sent in by some of you. The questions are addressed to Richard. Richard, you can read it from my screen. Could you give an answer to it?
Yeah, so I wasn't too sure if I understood the question. Question one, if we have already building and we can do the monitoring different in situ measurements, then why simulate and get more problem in the calibration? What would the simulation can produce more? I didn't understand that question, to be fair. So I don't know if someone can explain the issue. The second one, there's an open source project called Project Haystack, which may help you kind of address some of your queries there in terms of how you structure large pools of data across different buildings. I couldn't understand question 3, Hans. I don't know if you can.
Yeah.
I think question 3 goes with question 1. The question
Yes.
was,
Yeah, I thought so as well. Yeah.
a lot of monitoring and what is the input of the simulation.
Can do the
So
monitoring.
we need the simulation. We need the energy model to define what the building can perform like. So to things like legislation, regulation, things like this. So we need it to help our designers design buildings that work in real life and to make sure our carbon goals are met, that thermal comfort is met, and all other kinds of modeling issues like structural performance and things like this. There's lots of reasons why we should model buildings, but there's also lots of reasons why we should try and calibrate models, as you've mentioned, and that we should carry out verification that what we built on site actually works.
Yeah, I think that the person who raised this question should clarify a little bit better what exactly his intention is with this question. You need anyhow a model, so a model is simulating always. But okay, we invite the person who has raised this question. Please contact us again, one of us, Richard or myself, and we will try to give an answer to it. Okay. Then I think that I go to, if there are no other questions coming in, then I go and make a conclusion to this whole series of webinars. I do like, I prepared a short presentation. Let me see if I get it right. Okay, so let me start this conclusion of the 4 webinars that we have given starting from September, 4 weeks ago, 22nd, 29th September, last week, 6th of October, and today, 13th of October, on the subject of dynamic calculation methods for building energy performance assessment. The series of webinars were organized by Dynastee, and as I have presented Dynastee already in 4 weeks ago in my presentation from then. We are an informal network, Dynastee, so you can always contact us, you can follow us, you can get our information on all kind of things that we have been doing in the last 25 years. So we have data available, we have methodologies available, we have a lot of papers, articles, we have a lot of research activities, and the conclusions and reports of these projects. So you can always try to get this information from us by contacting us on dynastee.info on our website. The objective of Dynastee is therefore also clear, that we would like to play a role in this area on dynamic testing, and for so far we know we are quite a leading network. We are known all over the world. People are contacting us from Japan, China, Brazil, Canada, etc. So we give this information also to other people. What we try to do is that our knowledge that we have gathered over the last more than 25 years on performing tests, all the research work that we did in carrying out these experiments, collecting high performance, high quality data, and we have made this available to other people as well, and we like to maintain it. Also, one of the objectives is to bring industry and the academic world all together, and there are occasions that we are dealing also with experts from organizations like standard organization. We've been contributing in several projects. We have been contributing with our expertise. To say that we are at present we are still working in an IEA project, which is mentioned already several times. It's the Annex 71. That is the project that is about to be finalized. We might take part in a future project as well. Again, being an informal network that you have now learned to know about. We continue also to do the training on dynamic analysis. More or less the result of these webinars are a part of that training. Of course, we do also the training in the summer schools. We do also training in another format. In the past, we did some competitions just to challenge people to show their skill in doing the analysis on dynamic data. This course, well, if you can consider these webinars as a course, they are, of course, a very limited version of the summer schools that we usually are organizing. But the aim is the same. We have two objectives. Just to train the people a methodology. We do not say this is the best or this is the correct one. We will show the people always that there are different roads. Well, as we say, there are several roads to Rome. Well, we are convinced that there are several methodologies to get a certain answer of a certain quality. And that is why we would like to train different methodologies. The aim is always the same, to assess the thermal performance of a building. And a building can be a component of the building, an element of the building, like a wall or a window or etc. Or the whole building in itself. So the performance, the energy performance of the whole building. What we try to do also, and it is clear from our present situation on energy, we would like to understand how the future buildings, the nearly zero energy consuming buildings, how they really perform in practice, including the renewable energy technologies in the whole built environment. So it's already a discussion what exactly is the building when you have these kind of technologies just outside the building, in the field or on the roof, all these kind of things, how the performance will be. So the whole approach of our analysis is the combination of the knowledge on building physics, the knowledge and the application of mathematics and statistical methods. That is the most important part of our training that we would like to give. So here is a listing. You have seen this list already. Different topics that have been presented in the several webinars, or you can go through it. What we probably present more in detail during the physical summer school, that is more on all kind of uncertainty of the data, variability, the issue of not measured phenomena that are taking place in the whole energy concept of a building, and how to deal with that, and what exactly the measured data is presenting in what we would like to analyze. So there are that is more for the physical summer school, where we have also more closer contact with the participants than we have during the series of webinars. The people that have been over the last couple of years be involved in these kind of training activities, you see them listed here. We are quite a group, and we hope that we also will be present in the physical summer school that we probably may organize next year. We come back to that a little bit later. You always can contact these people directly. Most of them have given their email address in their presentations. I think that we have to thank all the people that have been presented so far, the presentations. I have here summarized a little bit the presentations that have been given by us. One of the things that I like to remind you is that a lot of the information can be found on our website, dynastee.info, including the data that have been presented. You can use it, and we ask you, if you make a publication using our data, please make a good reference to it. Where you have found this data, and that of course you can use it. Of course you can also use our methods, but be so kind to make a reference to it. So this is a listing of the presentations that we have done so far. So we have given you an introduction to the methods that we are using, in particular LORD and CTSMR. And we have given you also an introduction to the data that has been produced by PSA in Almeria. And that is of high quality, so you can use that. Of course, we have also now Richard has presented how metering data, what are the issues that are coming up with metering data, and we may go in the future a little bit more in that direction. Overall, after so many years that we have been given training to people, I think we have now more than 200 people had in our summer schools. What we have learned from it is that, well, you need really a skill to perform well in this kind of analysis. And we like to conclude with that as well. And we are thinking of organizing a kind of competition. I come back later on it, and probably you will find on our website also in the coming months more information about it. So you can feel free to participate and get it really a challenging task to perform or to show your skill in analyzing these data. So the conclusion that we have is really that training makes sense, and not only these webinars, but please continue in doing so. And if you have questions, you will always can contact one of us if you have a certain specific issue that you would like to have solved. These webinars have been attended by about 26 people this year. We hope that we get these number of people also in our physical summer schools. Usually we have around 25, and that is also our maximum of the people that we can handle. These summer schools, they are usually a week long. We will see how we will organize it for the coming year, but you will find out on our website. So this competition that I mentioned, we are thinking of organizing such again. That will be the third or the fourth competition that we organize. It might be this time that we will deal with metering data and with whole building measurements for analysis. But again, you will find out that on our website. So the future, well, last year we were not able to organize a physical summer school, and also now it is substituted by these webinars. But maybe Maria José, you can say something about the plans that we have to organize in Almeria the next summer school.
Yes, thanks, Hans. I just want to say that we are trying to organize it next year in Almeria, in the south east of Spain, and it will give us the opportunity to discuss more in detail everything, and we will have more continuous exchange of information between each other. So in principle, it will be in Almería and organized by CIEMAT in collaboration with the University of Almería and of course the Dynastee and INIVE. And we plan to be there 1 week, and the dates will be announced in advance in the Dynastee web site. So we hope that the situation of the pandemic will have a good evolution, so we will be able to be there and to see each other.
Okay, thank you. Probably we will announce it in January, in the month of January. So have a look by that time on our website. What will we do as Dynastee in the future and next year and maybe beyond? We will try to start several new topics. In particular, we'd like to create platforms for exchange of information on all kind of information that has to deal with renewable energy, how to deal with data from smart meters, from all kind of items like thermostats, like other sources of data, like weather stations, etc., etc. So we are looking into it, and we like to make always clear that we are dealing with dynamic analysis of these kind of data. We also have there is already some information about the project, the Annex 71, available on our website, or if you like to follow it closely, you may also find it on the IEA website. Just try to find the Annex 71 information, or you go to our Dynastee.info. Very soon, all the reports will become available, and you will find there also a lot of interesting information. There is also information available from the previous Annex 58, where we have also a number of reports available on dynamic analysis. So I invite you to have a look on the Dynastee.info website, or to the IEA Annex 58 or 71. I think that I come now to a few last slides. I would really like to thank Maria and Valerie for helping us to manage the series of webinars. Thank you a lot. And maybe we will have your support next year again when we are setting up the physical summer school. We will see how that is going. But again, thank you very, very much for this perfect organization of these webinars. And then I would like to finalize with the last slide here on Dynastee. This is our website. Here you can find on the menu item data analysis, all kind of information, and also all the presentations that have been given during these 4 weeks. You can find them, the presentations itself, but also the audio files. I think that these are my last words. Thank you, all the lecturers And I think that we will meet again somewhere in the near future. Thank you very much.